Okay, we resume with an example where we apply theorem 10.19 to compute the relaxation of a functional which we already saw in the past. So remember that in example 9.8, we consider this functional f defined from C1 of AB as the integral from a to b of u dot squared plus sine of u to the power of 5 in dx. So in that example, we showed and the goal of that example was to prove that this function here has minimizers which are C infinity. And the first step that we did was to extend this function to the space W12. And we did that extension more or less in an arbitrary way. And now we will show that actually the extension we defined last time is the one that comes from theorem 10.19. So, okay, first of all, notice that you can write the functional f as g plus h, where g is this first term here, so the integral of u dot square, which I wrote in this way. So it's the integral from a to b of psi of u dot, where psi of psi is just psi squared. And then plus h, where h is this other term. So it's the integral from a to b of sine to the u to the power of 5. Okay, now we notice that psi is convex. I mean, psi is just the standard parabola through the origin, and clearly satisfies the assumption of theorem 10.19 with p equals to 2 and a equals to 1 and b equals to 0. Remember, the assumptions was that psi of psi has to be larger than some a times psi to the power of p minus b. And in this case, since psi is equal to psi squared, you can just take a equals to 1, p equals to 2, and b equals to 0. Therefore, the theorem tells us that the relaxation of g, this function in L2, is just given by g bar, which is the integral from a to b of u dot squared if u belongs to W12 of AB, where again this is the weak derivative of the Sobolev function u, and plus infinity otherwise. So okay, from the theorem we know that this guy is the relaxation of this one, and by this we always mean that we first extend g of u to L2 by setting g of u equals to plus infinity if u does not belong to C1. So if u is only L2 but not C1. And instead for the other term, because we want to relax the whole functional f, so the other term, you have to notice that it's continuous in L2 of AB, and this is immediate to check by dominated convergence, for example. And therefore, since h is continuous, the relaxation coincides with itself. And I mean, this is true for semi-continuous functions. So if you have a function which is lower semi-continuous, then the relaxation is the function itself. And I will leave this as an exercise in the exercise course to check that this statement here is true in general. And then again, by another fact that I will leave as an exercise, if you have a function written in this form, where the first term, where one of the two terms, in this case h, is continuous, then the relaxation of the sum, so the relaxation of g plus h, is just equal to the relaxation of g plus h, because h is continuous. And again, I will leave this as exercise. So in total, we show that the relaxation of f is just the relaxation of g plus h, and showing therefore that f bar of u, defined by the integral from a to b of u dot squared plus the sine of u to the power of 5 in dx, if u belongs to W12 and plus infinity otherwise, is just the relaxation of f in L2 of AB, as we anticipated in the example. And again, doing that by the results we proved on relaxation, you also know that the infimum of f is equal to the infimum of f bar. So by doing this relaxation, we didn't change the value of the minimum problem. Okay. So now we dealt with the case of integral functionals of this form, basically, where psi is convex. Now I just want to give you a statement of what happens in the case when psi is not convex, but still satisfies the growth assumption from below, which was the growth assumption here. So a times psi to the power of p, absolute value, minus b. And this is what I want to do in the next section. So extension by relaxation on convex case. So as I said, I want to generalize theorem 10.19 to non-convex Lagrangians. And the first definition we need is the one of convex envelope. So given a function psi from R into R, the convex envelope of psi is the map psi star star. So this is just a notation. Psi star star defined from R into the extended reals in the following way. So psi star star of x is the supremum of g of x, where g from R into the extended reals is convex, and where g is less or equal than psi on R. So, okay, here you have a real valued function, and so we're saying that the convex envelope is just the supremum of, pointwise, supremum of all convex functions which are below psi everywhere in R. So in a sense, psi star star is like the largest. So the yeah, sorry, not the largest, but I mean basically the convex function which lies below the graph of psi. Okay, so let's see some properties of psi star star in proposition 10.21. So given psi from R to R, then we have that number one, psi star star is convex. So the convex relaxation is convex. Number two, we have that psi star star lies below psi in the whole R. And number three, we have that the supremum in the definition of psi star star is actually a maximum. So as a reminder here, I defined psi star star with a supremum. Actually, you can see that this is, it can be seen that the supremum is a maximum. And finally, 4 is telling you that the convex envelope can be written as the supremum of all the lines lying below the graph of psi, in the sense that, so this is an arbitrary line, mx plus q, but this line has to verify that my plus q is less or equal than psi of y for every y in R. So here, again, the definition here was supremum of all convex functions which are below psi, and you can replace this by just taking the lines which are below psi. Okay. And for example, I mean, just to have a pictorial representation of what is going on. So for example, this is a profile of a function psi, which is non-convex. And in this case, the relaxation coincides with psi in the parts of the graph where psi is convex, so these two parts. And instead, in this part of non-convexity, you just have to take pointwise the largest convex function, which is always below the graph of psi. And in this case, you just join these 2 points with a line. So psi star star would be this line between these 2 endpoints, A and B, let's say. Okay. So we don't prove this proposition. Proof is omitted, but you can find it in basically any book of convex analysis, like the ones I recommended in the bibliography. However, please don't. I mean, the proof is not included in the program of the course, of course. And with this relaxation, we can generalize theorem 10.19. And the generalization is given by this theorem 10.22. So let psi be a Lagrangian defined from R into R, and define the functional f from C1 of AB into R by setting f of u equals to, I guess, sorry, here I'm not making any growth assumption, so a priori this is with values in plus or minus infinity. But anyway, the functional f is defined as usual as the integral from a to b of psi of u dot. Then assume that there exists some exponent p in 1 plus infinity, endpoints excluded, and some constant a larger, strictly larger than 0, and another constant b in R, such that psi of psi is larger than a times psi to the power of p minus b for every psi in R. Then the relaxation of f in LP of AB, where the exponent here is the same as the one in the estimate, is given by this functional f hat, defined as the integral from a to b of psi star star of u dot, if u belongs to W1P, and plus infinity otherwise in LP of AB. Once again, so here we have the weak derivative, and this psi star star now is the conjugate, is the is the convex relaxation of the function psi. So the only difference with theorem 10.19 is that we dropped the convexity assumption, and in dropping that, we found that instead of putting psi in the relaxation, we have to put the convex envelope as Lagrangian. Now, I mean, this is not surprising because, I mean, in the sense you can also recover the statement of theorem 10.19, because if psi was convex, then for convex functions, one can show that psi star star is equal to psi. So if psi is convex, obviously the convex relaxation is equal to the function itself, because you can just take psi everywhere in the definition of the convex relaxation, because psi is convex, and obviously this is always satisfied. So yeah, psi star star is equal to psi if psi is convex, and therefore if psi is convex, here you can just have the usual psi of u dot. So the one we saw in theorem 10.19. The proof of this theorem is omitted, and I mean, it is similar. It can be done in a similar way to the one of theorem 10.19, just probably point 3 in the verification of the assumption of the strategy 2 is more delicate, but I mean, we don't have time to go through the details of this proof, so I decided to omit it, as all the main ideas are already included in the proof of theorem 10.19. Okay, so let's see an example of application of this theorem, and we apply to the double well functional that we saw already in many lessons ago. So consider the example of, the functional of example 5.6, which was defined as f from the C1 functions of a b into R as the integral from a to b of u dot squared minus 1 to the power of 2. Okay, so this is the function we considered and that we are considering now. The Lagrangian in this case is psi of xi. It's just equal to xi squared minus 1 all to the power of 2. And this Lagrangian clearly satisfies star with p equals to 4. So star was this condition, and the Lagrangian psi of xi is equal to xi squared minus 1 to the power of 2. And I mean, I don't want to do the calculations, but obviously this is equal to some, I mean, this goes like psi to the power of 4. Okay, so this is the highest power of psi that appears. So here you can, in this estimate, you can clearly take p equals to 4, and then, I mean, you have to find a and b such that this estimate with this guy here, so with psi replaced by the double well, holds. But I mean, then it just becomes an exercise of analysis I mean, not even analysis one, probably high school. But anyways, so the leading term is xi to the power of 4, so you're sure that you can find A and B such that this estimate is satisfied. And so the relaxation is ensured. I mean, we know how to compute the relaxation in W14 of AB. Okay. Okay, so this Lagrangian satisfies the double well potential here. So this is the profile of psi, satisfies star with p equals to 4 and some A and B. And therefore theorem 10.22 implies that the relaxation of f in L4 of AB is given by this function here. So it's f, so the relaxation is the integral from A to B of psi star star of u dot if u belongs to W14 of AB, and plus infinity otherwise in L4 of AB. Okay, and in this case, psi star star can be computed to be this function here. So as you can see in the region where the function, the double well is convex, so this region here and this region here, the relaxation is just the same as the original function, the convex relaxation, sorry. And instead in this region where you have non-convexity, you just replace this by the horizontal segment from -1 to 1, which is what I drew here. So this would be the convex relaxation of the double well potential, so of this potential here, which is written explicitly here. So you have your original function if psi is larger than 1, and 0 if psi is less or equal than 1 in absolute value. And if you remember, if you go back and look at example 5.6, this is exactly what we did to minimize this function under certain boundary conditions. So we just said, you remember we wanted to apply the trivial lemma, I suppose. And to apply the trivial lemma, we needed to find a functional g such that g was always less or equal than f, okay, and such that g of some point u0, which was a minimum for g, was equal to f of u0, and then g had to be convex, I suppose, or lower, yeah, or lower semi-continuous. Sorry, I'm trying to remember. No, none of that, sorry. G had to satisfy this assumption. So g less or equal than f, and that g was minimized in u0, and that f of u0 was equal to g of u0. And so that time f was given by this function, and g was given by basically by this function here. So this was g of u. We didn't call it relaxation, but now we know that g of u can be just taken as the relaxation, and it satisfies all the assumptions if you look at the general theorems that we proved. Because now here you have a convex Lagrangian, and so you can easily prove that this function here has a minimizer, depending on boundary conditions, of course. So in the case when it has a minimizer, you also know that this minimizer, because of the property inf of f equals to mean of f bar, which we proved in general, then you know that the minimizer you find for f bar is also basically a minimizer for f thanks to the trivial lemma. Okay, because in any case you know that you just need to verify that that f bar at the minimizer is equal to f, sorry, at the minimizer, because the property that f bar is less or equal than f, this is for free because we proved it in general. The relaxation is always below the original function. Okay, so this concludes with this example we conclude the section on relaxation, and we pass to a new section, which I hope we have enough time to talk about. And so the last topic of the course is gamma convergence. And we start with the definition. Okay, so we will set the gamma convergence in metric space. So let xd be a metric space, and assume given a family, a sequence of functions fn defined from the metric space into the extended reals, and a function f from the metric space into the extended reals. And now the goal is to define what it means that fn gamma converges to the limit functional f. So we say that the sequence fn gamma converges to f, and we denote gamma convergence with this symbol gamma on top of the convergence arrow. If these two conditions are satisfied. So the conditions are called gamma lim-inf inequality and gamma lim-sup inequality. The gamma lim-inf inequality says that for every sequence xn converging to x, and for every point x, so let's be more precise. So this is for every x in x, and for every sequence xn converging to the point, it holds that the limit, so f in x, is less or equal than the lim-inf as n that goes to plus infinity of fn of xn. So you have to evaluate the sequence fn in the corresponding point in the sequence xn converging to x, and then you take the lim-inf. If this lim-inf is larger or equal than f of x, then we say that the gamma lim-inf inequality is fulfilled. And the second condition is the gamma lim-sup inequality. So for every x in x, there exists a sequence xn converging to x such that the lim-sup for n that goes to plus infinity of fn of xn is less or equal than f of x. And again, here, notice that there is a difference between 1 and 2, other than here we take the lim-inf and here we take the lim-sup. The major difference is that here this condition has to hold for every point x and every sequence converging to x. Instead, for point 2, the gamma lim-sup inequality, you just need to check that for every point you can find one sequence such that this holds. So again, this is an existent symbol and not for all. So you just need to find one sequence, and you don't have to check this for every sequence. Basic remark is that if one holds, so if the gamma lim-inf inequality holds for every point and for every sequence, then if the gamma lim-sup inequality holds at a point x, this lim-sup is actually a limit. So here I should rephrase it in another way. So if 1 and 2 hold, so we remove these holds here, then the lim-sup in 2 is actually a limit. Okay, and this is because of the usual reason. I mean, you have that f of x, so assume that both hold, then this is obviously less or equal than the lim-sup as n that goes to infinity of fn of xn, and this is less or equal than f of x by the lim-sup inequality. So here you just show that lim-sup is equal to, lim-inf is equal to lim-sup, which is equal to f of x, and meaning that the sequence here has a limit, and the limit is just f of x. So in total, I mean, you have this condition, fn xn equals to f of x. Okay, notation, we call the sequences xn satisfying the lim-sup inequality. They're called recovery sequences. Okay. Okay, first of all, let's explore the connection to pointwise convergence, which is basically non-existent. So relationship of between gamma convergence and pointwise convergence. So let xd be a metric space, and f be a function from x into the extended reals. And then now consider the constant sequence given always by f. Okay, so this is a constant sequence. Then one might guess that since you're given the constant sequence, typically the constant sequence converges to the function itself, because you're not doing anything here. This is, so fn is always equal to f, so it's reasonable to expect might be reasonable to expect this result. However, this is not true, and in case of gamma convergence, you have that the constant sequence gamma converges to the relaxation. Okay, so let's see the proof of this. To check this gamma convergence result, you need to check that gamma lim-inf inequality and gamma lim-sup inequality are satisfied. So let's start with the gamma lim-inf inequality. And so we have to take any sequence, xn converging to x. Then we have that f bar of x, the relaxation. By definition of relaxation, this is just the inf of the lim-inf of f of zn, where zn is any sequence converging to x. Then, I mean, since xn is converging to x, this quantity here, this infimum, is less or equal than the lim-inf computed along the sequence xn. And now, since fn is constantly equal to f by definition, by assumption, this is just the lim-inf as n that goes to plus infinity of fn of xn. And so this proves the gamma lim-inf inequality, because we've shown that for any sequence xn converging to x, f bar of x is less or equal than the lim-inf, the less or equal is here, less or equal than the limif as n that goes to plus infinity of fn of xn. And now we just need to check the gamma lim-sup inequality. So let x in x be arbitrary. By lemma 10.8, we know that there exists a recovery sequence for the relaxation, and the recovery sequence was defined as so we know that there exists some sequence converging to x, such that the relaxation is just the limit as n that goes to plus infinity of f of xn. Now, since fn is equal to f by definition, we conclude, because this will be then again equal to the lim as n that goes to plus infinity of, so equals lim n goes to plus infinity of fn of xn. And this is the gamma lim-sup inequality verified with the limit, because, I mean, anyways, this is equal, obviously, to the lim-sup of fn of xn, because this sequence is convergent by lemma 10.8. And so we prove that the constant sequence gamma converges to the relaxation. And this proposition is actually telling you that, so this is what we are saying in this remark, in the following remark here, proposition 11.12 is telling you that gamma convergence is not related to pointwise convergence, so not related. And this is because, okay, if you take the constant sequence with f such that f is not equal to the relaxation, then obviously you have that fn converges to f pointwise, because fn is the constant sequence. But then fn does not gamma converge to f, because by the proposition we just saw that fn actually gamma converges to the relaxation, and we're assuming that the relaxation is not equal to f. So in the end, you have that fn does not gamma converge to f. I mean, this also, this is assuming that we prove that the gamma limit is unique, which is easy to check. So if the gamma limit exists, then it is unique. And on the other hand, by the proposition, we have that fn gamma converges to f bar. This was proven, but obviously fn is not converging pointwise to f bar, because fn converges pointwise to f, and f is not equal to f bar, and the pointwise limit is unique. So, okay, just to underline this fact, because gamma limit is unique. And this is because pointwise limit is unique. Okay. However, under additional assumptions, we can see that uniform convergence implies gamma convergence. Sorry, there is a typo here. Uniform. And this is exactly the statement of proposition 10.3, which tells you that in the usual setting, so XD metric space and sequence of functions and candidate limit defined from the space X into the extended reals, then assume that 1 Fn converges to F uniformly on the compact sets of X, and 2, assume that F is lower semi-continuous with respect to the metric D, then it is true that Fn gamma converges to F. So I'm not going to prove this proposition now, rather I will leave it as an exercise to prove this statement. And so just to recap, this is telling you that if you have uniform convergence of compact sets and the candidate gamma limit is lower semi-continuous, then you actually have gamma convergence. And so in light of proposition 11.2, yeah, sorry, this here I made a mess with the notation. This should be 11.3 and not 10.3. So in light of proposition 11.2, clearly here, if you assume that 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 f is lower semi-continuous, then you can see that for lower semi-continuous functions this is true, and so this is just telling you that f, this constant sequence, gamma converges to the function itself if the function is lower semi-continuous. Okay, so this is the relationship with pointwise convergence. And now just if we say it like this, it seems like gamma convergence is a trivial tool, because we're saying, okay, if we have uniform convergence on compact sets and the limit is lower semi-continuous, then this already implies gamma convergence. The point is that in general, when you're given a sequence of functions, you will not have that this sequence converges uniformly to something. So you will actually have to relax the notion of convergence, and the right notion is the one of gamma convergence. So stability properties. So this could be another section actually. Stability properties. Sorry. Okay, so stability with respect to continuous perturbations. The first proposition, again, sorry, the notation is, so the numbering here should be 11.4. And again, here I made another mistake. This should be 11.5. But anyway, so XD metric space, and as usual, Fn sequence and F candidate gamma limit. Assume that Fn gamma converges to F. So now suppose you're given another function g from X into R, which is continuous. Then basically Fn gamma converges to F implies that Fn plus g gamma converges to F plus g. So here we're just saying that if you have a sequence which gamma converges, and you add to this sequence a continuous perturbation, so Fn plus g, then the gamma convergence result is that Fn plus g gamma converges to F plus g. So meaning that the gamma convergence is stable with respect to the addition of continuous perturbation. And the proof of this proposition 11.4 is a consequence of proposition 11.5 below, which says something slightly more general. So proposition 11.5 says that usual setting XD metric space Fn and F defined from X into the extended reals, and assume that Fn is gamma converging to F. Then suppose that you're giving a sequence Gn and a function G such that 1, Gn converges to G uniformly on the compact sets of X, and 2, G is continuous. Then Fn plus Gn gamma converges to F plus G. So this is telling you something more than proposition 11.4. It's telling you that if you actually have a sequence here, which is converging uniformly on compact sets, and the limit is continuous, then this does not alter gamma convergence. So basically you just take the gamma limit here and the pointwise limit here, and you obtain the gamma limit. And the proof of this proposition, I will leave it as an exercise for the exercise course. And I mean, if you notice, obviously this immediately generalizes proposition 11.4, because you can just take Gn constantly equal to G. Then in this case, number one is obviously satisfied because the constant sequence converges uniformly on compact sets to the constant function G. And number two, G is continuous. We are already assuming this in proposition 11.4, and therefore you obtain that Fn plus G gamma converges to F plus G, as was given in the thesis of proposition, what was the proposition? 11.4. Okay, so this is the notion of stability, so for that I wanted to give you for gamma convergence. And now it is useful to introduce basically the equivalent of the lim-inf and lim-sup in the case of limits, the equivalent with respect to gamma convergence, because as typical with limits, also gamma limits don't always exist. So for this reason, it is useful to introduce gamma lim-inf and gamma lim-sup, which are objects which are always defined, as it is true for lim-inf and lim-sup of sequences of sequences in R. Okay. So let's start with the definition of gamma lim-inf and gamma lim-sup. And again, sorry, here I really messed up all the numbering. This is 11.6, this is 11.7. Okay, definition: given a metric space XD and a sequence from X into R extended reals, we define the gamma lim-inf of Fn. So this is just a notation, and so remember that this notation means that so gamma lim-inf and that goes to plus infinity Fn. This is just a notation, and this is defining a function from X into the extended reals. Okay, so we need to define, so it's like if we call this function G, for example. And now I just have to tell you the value, how I define this function for every point X in X. So, okay. So, okay, the gamma lim-inf at the point X is defined as the infimum of all the lim-infs of the sequence Fn evaluated on sequences Xn, such that Xn is a sequence in X and Xn is converging to X. So, okay, here I'm just basically doing the worst, the worst I can do in the gamma lim-inf inequality, because remember, in the gamma lim-inf inequality, I had to find a limit f, gamma limit f, such that this was less or equal than this quantity for every sequence converging to X. Here, I'm just saying, maybe I'm not able to find this f of X, but anyways, I can always consider the infimum of this quantity along all the sequences converging to X. And I define this to be the gamma lim-inf of the sequence Fn. And similarly, I define another function on the space X, which is the gamma lim-sup as n that goes to plus infinity of Fn. And for a fixed point in X, this is defined as the inf of the lim-sup of Fn of Xn along all the sequences in X which converge to the point X here. So, okay, as I was saying, these two objects here are always well defined, given a sequence of functions on your metric space. Okay. Okay, so this next proposition, 11.7, is telling you that basically gamma lim-inf and gamma lim-sup behave exactly in the way they should. So imagine that consider this proposition without the gamma here, just with liminf and linsup, and imagine that these are sequences of real numbers. Then basically you can just remove all the gammas in this statement and all the dependencies on X. And this is exactly what you would expect from a definition of a liminf and of a linsup. So usual setting, XD metric space, Fn sequence of functions. Then the gamma liminf of Fn and gamma linsup of Fn always exist, so they are well defined, and they satisfy this inequality here. So the gamma liminf is always less or equal than the gamma linsup for every x in X. And second part of the statement instead tells you that Fn gamma converges to F for some gamma limit F defined from X into the extended reals, if and only if gamma liminf and gamma linsup coincide. So basically this is telling you that this inequality is always true, and whenever you're able to prove that these two guys are equal on the whole space X, then you can identify a gamma limit for your sequence. And this is true. This is an if and only if, in the sense that Fn gamma converges to something if and only if this equality holds for every point X in X. Okay, let's check the proof of this proposition. Here I'm saying that the first part of the statement is trivial because, okay, from what I observed, if you look at the definitions of gamma liminf and gamma linsup, obviously these are always well defined, possibly being equal to plus or minus infinity. And also this inequality is obviously true because if you just look at the definitions, this is the inf of liminfs, this is the inf of linsups, and so pointwise you have that. Pointwise, I mean for every fixed sequence, you clearly have that this liminf is less or equal than the linsup. So now you can just take the infimum of on the left hand side and on the right hand side, and you conclude that gamma liminf is less or equal than gamma linsup. So the only thing that we actually need to prove is the moreover part of the statement, so that Fn gamma converges to F if and only if star holds. So assume first that you know that Fn converges to some gamma limit F, and now we want to check that star holds. So take any sequence, Xn converges to X, then by the gamma limit inequality, which is ensured by, which holds by, since we're assuming gamma convergence, we have that f of x is less or equal than the limit Fn that goes to plus infinity of Fn of Xn. And therefore, if you just take the inf on all the sequences Xn going to X, so the left-hand side is unaffected because this does not depend on the sequence, so you recover it here. And instead, on the right-hand side, if you take the infimum, you find you recover the gamma limit. So Fn gamma converges to F implies that f of x is less or equal than the gamma limit of Fn of x for every x in X. Second, on the other hand, let's do it like this. On the other hand, the gamma linsup inequality says that for every x in X fixed, there exists a recovery sequence such that the linsup of Fn of Xn is less or equal than f of x. And therefore, by definition of gamma linsup, again here, so this is just one sequence, then I can just go down in the inequality if I say that this is the infimum along all the sequences, and this is exactly the definition of gamma linsup. So from the gamma linsup inequality, we basically obtain this estimate here. So the gamma linsup is always less or equal than the gamma limit for every x in X. And therefore from 1 and 2, so 1 was telling you that f is less or equal than the gamma limit. This is telling you that the gamma linsup is less or equal than the gamma limit. And then by chaining these two inequalities, you see that gamma linsup less or equal than f, and so gamma linsup less or equal than gamma limit, which is what I wrote here. So gamma linsup less or equal than gamma limit, and this is true for every x in X. And since the other inequality is trivial, or more or less, I mean trivial in the sense it's was already proved, in the first part of the statement. We conclude star. Okay, so the other inequality being this one, that gamma lim sup is larger or equal than gamma lim inf. And this we saw that is, in the first part of the statement, we say that this is always true. So now we just proved that Fn gamma converges to F implies that gamma lim inf is equal to gamma lim sup. And now we have to prove the other implication of the if and only if. So the other implication, assume star. So assume that gamma lim inf is equal to gamma lim sup. And obviously, let's define a candidate gamma limit. And the reasonable candidate gamma limit is just defined as pointwise as the gamma lim inf, which is also equal to the gamma lim sup since we are assuming star. So they define f of x as the gamma lim inf as n that goes to plus infinity of fn of x, and we want to prove that fn is gamma convergent to f. So we need to check gamma lim inf and gamma lim sup inequality. Let's start with the gamma lim inf inequality. So take an arbitrary sequence xn converging to x. Then we have the lim inf of fn of xn. This is always larger or equal than the gamma lim inf because of the definition of gamma lim inf. Remember, it was defined as the infimum of this stuff among all the sequences xn converging to x. So this is always larger or equal than the gamma lim inf, and this is equal to f by the way we defined f here. So we discovered that f satisfies the gamma lim inf inequality. Now let's check the gamma lim sup inequality. And so for the gamma lim sup inequality, fix some arbitrary x in x. Now you have to check that if x since star holds, so since the gamma lim inf is equal to the gamma lim sup, then you can find a sequence such that xn is converging to x, and these two quantities are the same. So the lim inf is equal to the lim sup, and they're equal to the gamma lim inf and the gamma lim sup, and so they're equal to f by definition. Okay, so this shows that you can find a recovery sequence such that the lim sup is equal to f of x, and this concludes the proof of the reverse implication. Okay, so here I should maybe be more precise. I should say that, so actually you prove this one, and in particular you see that by definition of f you conclude. Okay, so I think that let me check the time. Okay, we are at the end of the lesson. Next time we will resume with the gamma convergence, and probably, I mean, if I have enough time, I will give a couple of results, and that will be our final lesson of the course. So okay, see you next week.